All right, welcome to the first afternoon session today of APLAS. Our first paper will be RHLE, Modular Deductive Verification of Relational for All Exist Properties, and Robert Dickerson will give the talk.
All right, thanks. So I'm Rob. I'm going to be talking about modular deductive verification of relational for all exist properties. So this is work with Shen Chuanya, Michael Zhang, and Benjamin Delaware at the Programming Languages group at Purdue University. So the title is a little bit of a mouthful. I want to sort of start with an example to illustrate what we're up to here. So on the left, we have a program called sample1 that has an array, and it's getting randomly sampling elements out of the array using this bounded random number generator and some array index manipulation. And I want you to imagine that someone has come and decided to rewrite this so that instead of using array indices and random number generators, it's using a list API that exposes a permute operation, which will shuffle the list around, and a sublist operation. And our goal is to verify, hopefully automatically, that this rewrite hasn't introduced any new behaviors. So everything that sample2 can return, sample1 could have returned. Okay, so a few things to note. We have some calls to functions here, whose bodies we haven't given. And we want to do the reasoning without bodies, but with specifications instead. This is a natural thing to want to do, especially with APIs, where the whole point is you can swap out different implementations. So we want to reason against specifications. The specifications might allow for multiple behaviors, so this is something to keep in mind. Obviously, with random number generator, it should allow for lots of different random numbers. For permute, it should allow for different strategies to do the permutation, etc. Okay. So that's what we meant by modular, that we have this layer of modularity with this function specifications. By deductive, we mean that we want to do this with a Hoare-style program logic. So we have precondition and postcondition. We want to step over the program syntax and in order to verify these properties. By relational, we mean that the pre and post conditions are going to have to talk about state from different executions. So if you want to say that we're starting these two programs, we want to, maybe our precondition is that the inputs are the same, right? So this is going to have to talk about state from multiple executions. That's what we mean by relational. And by for all exist properties, we mean properties with this general shape, where we want to say for all executions of some programs, there exist executions of other programs that give us the post condition that we're looking for. So we're going to have to guarantee the existence of some desirable executions when we do this. So for this example here, we have for all executions of sample 2, we want to make sure there exists an execution sample 1 that gives us the same result. This property is called refinement, by the way. So here's what this looks like visually. We have different program executions. We're dividing them up into sort of for all land and exist land. And we're saying that we're going to draw a box around the preconditions and say, okay, we have to start out in some state that meets a relational precondition. And then we're going to step forward going from state to state. Sometimes we might have branches where, well, depending on what the implementation of some method does, we can maybe do different things. But for all land, whenever we get to the final states, any possible thing we can reach had better meet the post condition. Whereas in exist land, we only need at least one final state to meet the post condition. Okay, so how are we going to write this down in sort of a Hoare logic way and have logics that operate and let us prove these kinds of properties? So the way I'll proceed with the talk is I'll talk about how we will show things in for single execution. So when we're in for all, we have a for all program. How do we have a logic that lets us just reason in this way universally? How do we have a logic that lets us reason this way existentially about a single execution? And then I'll talk about how we combine those into a relational logic, and then I'll talk about how we turn that into a verification algorithm. Okay, so to start single universal executions, this is just the semantics we want here is just standard partial Hoare logic. So we want to say that when we start in the right precondition, no matter what states we end up in, it's going to be within the post condition. So we can use partial Hoare logic as our starting point, but we need to handle these calls to functions with specifications. So how do we do that? Well, first, how are we going to write down the specifications? We'll write them this way. So this is saying that we have a function f that has some arguments x bar, and then we have a pre and a post condition. The precondition is allowed to talk about the arguments. The post condition is allowed to talk about the arguments, as well as the return value. And throughout the talk, we'll use rho as this distinguished variable to represent the return value. Okay, so what does this look like? Well, here's a specification for our bounded random number generator. It's going to take a single argument x. Its precondition is unconstrained, and its postcondition says the return value has to fall within the range. We're going to put these specifications in the specification environment, which is just a mapping from the function name to the specification. And this environment is going to live sort of on the left-hand side of our turnstile as we talk about these triples and how they operate. We want to reason about them, and we need access to the specifications. So here's an example of a triple that should be valid. We expect it to be valid. It's pretty simple. We're just calling rand b with x. X has been assigned 10, and we want to say that our return value for this program in the box is always less than 20. Since our return value is always less than 10, we expect this to be valid. So like I said, we're going to start with standard partial Hoare logic. We need to augment it with this rule. Don't worry about trying to parse the rule live here on the slide. The important thing to note is that we have this universal quantifier on the left. So we want to show that there's some post-condition R that we're meeting. We need to show that the precondition is met, and any possible value that meets the function's post-condition should be sufficient to establish this overall post-condition R that we're going for. Okay, so that's the universal Hoare logic. What about the existential single execution Hoare logic? Well, remember, our goal is to show that at least one execution ends in a desirable state. So we need to be making a guarantee about the existence of some final state that we want. This sounds like total Hoare logic, so we're not allowed to like loop forever and never end or whatever. We have to guarantee that we're going to end in a final state. That's what we want. So we're going to use total Hoare logic as our starting point here. Like with the universal case, we need to worry about specifications. So specifications here on the existential side, remember, we want to make guarantees about the final states that we can end up in. So our specifications are going to need to make guarantees about final states that are possible. So the key idea is that we're going to take these decisions that implementations of these specifications are allowed to make, a simple example being which random number to return. And we're going to reify that into what we call choice variables. These look like program state that the pre and post condition can refer to. It's basically ghost variables for the specification. So an example might be the best way to sort of see how this works. So here's the existential version of our rand b specification that's guaranteeing any return value in the range is possible. So we identify a single choice variable c. In the precondition, we constrain c to be between 0 and x. And then our post condition is going to be the return value is that c. So here's an example of an existential Hoare triple that we want to be valid. The post condition here is that we've returned 3. In order to say that return 3 is a possible final state, we need to know that rand b can possibly return 3. And it can, because you can pick a c, namely 3, which meets its precondition and gives us the post condition that we need to establish our overall post condition. So important to note is that if we had a rand b implementation that, for example, always returns 0, it won't meet the specification because there is a precondition. You can pick c as anything non-zero, and the precondition will be met, but the post-condition is not possible, so that would meet it. And also we can use, we picked 3 here, but obviously any number from 0 to 10 should work. Okay, so something that's important about this as well is that these choice variables are corresponding directly to the branches when we think about how these states are transitioning, and we say we have choices for which state we're going to go to next. Picking a choice variable corresponds directly to picking a branch in this execution. So the game for verification becomes finding strategies for picking these choice variables that sort of maneuvers you into the right branches to get you to the end state that you need. So this is a pretty short one. We're just basically flipping a coin, rand b2. And we want to show that the return value is 1. So we need to pick a C that lands us in the right execution branch. So in this case, it's pretty straightforward. Okay. So that being said, our existential Hoare logic now is rules just for the standard total Hoare logic. And we're going to add this rule for specification. Again, if you don't worry about parsing this directly unless you feel like a challenge on the slide, but the important thing to note is that whereas in the universal rule, we had a universal quantifier, here we have an existential quantifier. In the universal rule, the universal quantifier was saying no matter what return value you get that matches the function's postcondition, should establish the overall postcondition. Here we're saying that you should be able to pick choice variables that you can plug into the postcondition that meet the precondition and establish the overall postcondition. Okay. So we have logics for sort of reasoning in this universal way and reasoning in this existential way. How do we stick them together into a relational logic so we can prove these types of for all exist properties? Well, remember, a relational property is going to, we're going to have multiple executions. We're going to be able to talk about groups. We're going to group initial states, group final states, and have postconditions that can refer to values in all of these states. So our example from the top, the relational precondition says that the inputs to these two things are equal. The relational postcondition says that the outputs are equal. But remember, we want to do this in a for all exists way. So it doesn't need to be the case that every execution of sample 1 matches what we got in sample 2. And there's random numbers random number generation happening. So that's not going to work. We need to say that there exists at least one. Like if the random number generator turns out the right stuff, then the samples will be equal. Okay, but if you look at the literature and people who are looking at relational Hoare logics, they're mostly looking at case safety properties. So here are a few relevant citations. This first one is sort of a seminal paper on relational Hoare logic by Nick Benton. Barth and others have done a lot of work on using product programs to do this type of verification. There's a paper in PLDI 2016 with Susan Dillig created this Cartesian Hoare logic, which is used to verify these kinds of case safety properties. And a case safety property is a generalization of the safety property. So a safety property says you start at a safe spot, you're always going to end in a safe spot. This is just saying, okay, now you multiple executions. If this is a 3 safety property we have illustrated up here, if all 3 starting states are within the precondition, then no matter what end states you get to, they're all going to land within the postcondition. But remember, this isn't what we want. We want something that looks like this. So we want to divide up our programs into a for all world and exists world and say that, well, okay, every for all program final state needs to be in the postcondition, but only one final state for each existential program needs to end up in this postcondition. Okay, so how do we do that? Well, first we need a way to write down this kind of property. And here's the way that we write it down in RHLE, which is our logic for working with this with these kinds of properties. It stands for relational Hoare logic with existentials. The notation is sort of borrowed from from Cartesian Hoare logic, but going from left to right, it sort of looks like this. So on the left side of the turnstile, we have universal and existential specification environments. We're going to reason in both modes, so we need access to both kinds of specification. Then we have the turnstile. Then we're going to give a relational precondition. Then a list of programs that are for all programs, so living on that top part of the line of the for all side. And we're going to separate them with this circled asterisk. This is just a syntactic delineation between the programs. We're going to separate those with a tilde, and then we're going to list their exist programs, and then finally the relational postcondition. Okay, so using this triple, whatever you want to call it, relation, here's some properties that you can express. So we already talked about refinement. We want to show that, okay, you start in states where the inputs are equal and for all exists, end in a state where the outputs are equal. Observational equivalence, refinement in both directions. Generalized noninterference is secure information flow property that's basically saying if you have a public output of some function that uses secret state, for any other secrets, it should have been possible to get to that same output. That way you haven't sort of leaked any information about your secret. You can express that as well. It's also interesting to think about what happens if you sort of blank out one of the sides. So here we have a sort of a kind of non-determinism property that doesn't have any universal executions. It just has 2 existential executions and says that there exists 2 executions that where the outputs aren't equal. And if you sort of blank out the existential side, you fall back to case safety properties. So this logic becomes basically Cartesian Hoare logic of Susan Dillig. Okay, so now that we can write down these properties, how do we reason about them? Well, the logic that we present really is, it's too much to go into in this talk, so I'll refer you to the paper for the full logic. But a couple of important features. Remember, we want to reason deductively by stepping over program syntax. So how do you do this? Well, we have 2 different step rules, one for the universal case, one for the existential case. And the important thing to note is that when we take a step on the universal side, we're going to discharge our new, when we step to a new precondition, we're going to discharge that to the universal Hoare logic for single execution. When we do it for the existential side, we'll use the existential logic, and that's how those two single execution logics fit together into the relational logic. We also have rules for synchronized reasoning over executing loops in lockstep for different executions. So again, this is a little involved to get into in the talk. Please see the paper, but these kinds of rules are important for relational logics. They make it more efficient than, for example, product program approaches because it greatly simplifies the state space that the verifier has to consider. It also greatly simplifies coming up with invariants. Okay. A couple of key theorems from the paper I wanted to highlight. These are theorems that we've verified in Coq. Firstly, remember we're reasoning against these specifications. We're going to eventually link in implementations that meet the specifications. So it had better be the case that whatever properties we established when we reasoned with the specifications, they should still hold when you link in implementations that meet the specs. So this is theorem 1 and 2 in the paper. We also have a soundness result for really. This is theorem 3 in the paper. We have a completeness result on pen and paper, but it's not verified in Coq. All right. So we have this logic really that lets us reason about these for all exists properties. How do we turn this into a verification algorithm? So note that the call rules from our single execution logics are sort of written in this backward reasoning style where we have just some arbitrary post condition R, and then on the left we have some blob of stuff that you need to have in order for R to be true. So this very naturally translates to a weakest precondition semantics. So we use the standard weakest precondition semantics for universal for total and partial Hoare logic, augmented with these rules. And then we, for verification, we start stepping over program statements on existential universal side, discharging verification conditions with these using this weakest precondition semantics to an SMT solver. So note that these verification conditions are going to contain existential quantifiers potentially if we've stepped over existentially quantified calls. So remember I said the game with verification is basically deciding how to instantiate these choice variables so that you end up in the right branch of program execution. What we're saying here is that this sounds like a job for the SMT solver. We'll give it verification conditions with existentials and let it work out how to plug these in. The downside, obviously, is that if you're in a theory that doesn't have a complete decision procedure for existential quantifiers, then the verification may not be complete. Okay, so we implemented this verification algorithm in Haskell, a tool we call RHLE that uses Z3 as its backing SMT solver. It's available on GitHub. We ran it over a suite of benchmark programs that some of them we came up with ourselves, some of them are from the literature. Some of them are expected to verify, some of them aren't. We got the expected result for all of them except one of our program refinement examples gave us an unknown. This was because the verification conditions fell out of outside of the decidable fragment of arithmetic. I'll also note that we ran it on a couple of benchmarks that have just an exist shape to test the existential logic along this one. Okay, so to summarize, we think there are many interesting properties that you want to verify that have this for all exist shape. We have function specifications, and a lot of these properties we naturally want to reason over functions via their specifications. And this gives us some branching behaviors to consider when we do the verification. When we reify choices that implementations get to make into the specifications, that unlocks this deductive verification technique for all exist properties. We created a program logic called RHLE and a verification algorithm called RHLE to do this verification and ran it on a suite of benchmarks. The code is available on GitHub. So with that, thanks for your attention, and I'm happy to take questions. Yes. Oh, do you need the mic? How does this work?
And off the mic.
Okay.
Okay. Thanks. What about netting quantifiers? I want to go beyond just one level.
Yeah, so if you want to start alternating quantifiers for all exists, I don't think there's any reason that you couldn't do that. We haven't found a compelling property where you might want to do that. But if you did, you could, I think you could start constructing relations that are for all exists, just keep nesting quantifiers all you want, stuck over in the same ways, and I think it should work. But we haven't really investigated that fully, and like I said, mostly just because we haven't found the motivation to do
High
that.
order functions and stuff.
Sorry?
If you use high order functions, you stuff.
Right. So we've been looking at a very imperative style programming language, so we haven't considered higher order functions. But you might be right, that might be an interesting case for doing that.
You can run around with those if you like.
Thank you.
I'll wait my turn.
Oh,
Okay, that's okay. It's good.
you can use that one maybe.
Oh, yeah.
So you talked about loop synchronization, right?
Uh-huh.
Programs run in lockstep. Now, I think it's often the case that when you have two programs and you want to verify this kind of property,
Mhm.
they're actually not wanting to run in lockstep, right?
It depends. So sometimes running in lockstep is useful, and other times it isn't.
So you also have an option to go desynchronized, basically.
Yeah, so the way the verifier works is it will try to do things in lockstep, and if it can't figure out a good alignment or it can't, then it will fall back to doing it, stepping over one loop, then stepping over the other loop, not doing it synchronous. It is a difficult problem for figuring out that alignment. That's like a whole other can of worms, and I think there's some interesting future work to be done there. So.
All right, thanks for the interesting talk. So I don't get the part about the total Hoare logic, because here what you want is to have the existence of an execution, right, of a state. But by total Hoare logic, do you mean Hoare logic with total correctness? And because if so, I don't see how that would work with non-determinism.
Yes, so the only non-determinism comes from the function calls and the way that we have things set up. When I say total Hoare logic, I just mean you're not allowed to establish the property by just having the program like loop forever and never terminate, right? So if you sort of ignore the non-determinism and you just think about what we were trying to show in the existential case, is that we are guaranteeing you get to a desirable end state, right? So if you imagine there's no determinism at all, you just want to show guarantee get to an end state. That's something you have to show with total Hoare logic, because you don't want to allow like looping forever to satisfy that property, right? Which a partial Hoare logic would. Does that answer the question?
Yeah. So if you want, let's say I want to model an input or something with your logic, I would have to go into having a function and an existential specification. I couldn't have, for example, a havoc in the programming language.
Yeah. So the way that we have it, the way that we have it set up here is that there is no havoc. But if you wanted a havoc, you could write a specification to a function that is basically the specification for havoc. And I mean, even if you didn't have yes, I guess the short answer is yes. You would have to go through the hoop of implementing havoc. I mean, I think you could put havoc natively into your language and then add some rules to the Hoare logic to reason about havoc. That would basically look like the function calls. But yeah, I think you could do that. Yeah.
So you use run as an example.
Uh-huh.
Maybe it's not a deterministic choice.
Uh-huh.
It's not about actual probabilistic choice.
Yeah. So we haven't. So this doesn't address probabilistic choice at all. So if you want to have a property, which is very reasonable, if you want to say that, like, well, not only do I want to guarantee that every number in our range is possible, I want to guarantee that it's like uniform, like, the distribution, guarantee something about the distribution. This isn't talking about that at all. So if you wanted to add that in, I think it would be interesting to try to do that, but we haven't tried to do that.
By the way, for those connecting online, we do have a way of getting your questions. So go ahead and post them if you have any.
Just going back to the double random example, I just want to make sure. So just because I don't think you said this explicitly, but it's refinement in one direction, but not the other, because one of them is sampling with replacement, one that's without, right?
Exactly. Yeah. I think it's cool that you noticed that, by the way. So yeah, going back to the very beginning. I don't know if there's a quicker way to have done this. Yeah. So if you're keen-eyed, you might notice that when I'm sampling on the left here, I'm sampling with replacement. I can sample the same things out of the array multiple times. But on the right here, I'm shuffling the list and taking a sublist, no replacement. So yes, the refinement, if you tried to show refinement in the other direction, it won't work.
So I guess the follow-up is, are you able to express the property of for every on this side, you have exist on this side, and for every on this side, you have one on that side?
So you could write down those two triples separately and prove them separately.
I
So if
see.
you wanted to show like observational equivalence, that you could do it that way.
Okay, thank you.
Great. Any other questions? All right. Well, thank you very.
All right,
very
thank you.
much.